Welcome to the third lecture of our series on probability and stochastic for finance. Let me tell you that from this lecture we are getting more and more immersed into the deeper theory associated with probability. The last two classes were much more of developing an insight. Of course, I expect that the course that you are now taking would be some sort of a second course for you rather than just a first course, because the first course needs more detailing, which is not possible in the set of 10-hour lectures, and it is essentially a pre-runner to the course on derivative pricing in financial markets. So, it is better for me today to tell the book that I will be using from this class onwards till the end of this course is a book called An Introduction to Stochastic Differential Equations by Lawrence C. Evans. So, this book is published by the American Mathematical Society. I do not expect you to have this book with you, but I will in general follow this book, except maybe a little bit of material taken from some other sources. Maybe I should just show you the book in case you want to see the cover, that it is better to show you the cover in detail. This is the book which I will be largely using in this course, and as I have told, from today we are really going to get into the more theoretical issues. We will immerse more into the technicalities of probability theory. So, one of the first set of technicalities that should come is the idea of a random variable or a random vector. Random variable slash a random vector. So, we will explain both these concepts. Of course, those of you who have got a basic course in probability, you would know that random variable itself is a slight misnomer because they are actually functions. But in a standard probability course, you are being told that a random variable is nothing but a mapping from a sample space to the real line. But there are certain other properties that needs to be attached to such a function in order to call it a random variable. So, let me consider a probability space and a probability measure P, and also consider the real line R and a sigma algebra B. On the real line R, the sigma algebra that we have associated with R is called the Borel sigma algebra, which is naturally related to its topology. This Borel sigma algebra consists of all open sets, hence all closed sets, all half open intervals, half closed intervals, open intervals, closed intervals, and so on and so forth. So, it is the collection of all. So, it is the smallest sigma algebra which contains all open sets in R. In fact, it is the smallest sigma algebra which contains all open intervals in R. You can just think of it like that. So, this is the information that we really need. Essentially, random variable is a way in which outcome of a random experiment is translated into a number, and a outcome of an event is translated into an interval. That is the essential idea. So, interval or union of intervals. So, X is called a random variable if it is a mapping from omega to R, but with the following property, that if you take any B which belongs to the script B, the Borel sigma algebra, this is not the standard B, this is the script B. If B belongs to the Borel sigma algebra, then the inverse image of the set B must belong to the sigma algebra U. So, in this case X is called U measurable or just measurable. So, this property has to hold. If you can define a function for which this property holds, then we called X is a random variable. So, this property is called the measurability property, that inverse image of an event in the domains in the range space is also an event in the. So, if you take an event in the domain range space and pull it back, take the inverse image, then it will map to some event in the actual space, the decision space or the domain space. So, why so that is why this what does this idea tells you? This idea tells you that every every event is actually related to some interval here or some union of intervals, some set here. So, that is why when you pull back, take a set from here and pull it back, it will always map it back to an event. So, an event is taken to another event, but in the space R. So, this is something very important, that so every event is taken to some sort of an interval or union of intervals. That is the idea. That is the key idea behind introducing random variables. So, that is the key idea behind the notion of a random variable, that an event here has to be always taken into an interval in the real line. So, we map an event to a interval. So, we can now handle real numbers which are much more easy to handle, instead of handling events which may consist of arbitrary things. They may consist of set of all dice that you have thrown, outcomes of a dice or outcomes of a coin throw, or you are arbitrarily randomly choosing points from a rectangle, for example. So, that arbitrariness of the events, because these are very different random experiments, are being taken to a common thing, are being mapped to something which is common. So, all studies of probability can be now done in the settings of real numbers. This idea can be extended, and it is useful in some cases in finance to look at this extended idea of a random vector, where you have the same setting okay, and in this case you even need not bother about any probability measure, you can just forget it, you can just look into this measured space. And you can now talk about, maybe I will just write it like this. So, this sort of thing so this B associated with Rn, so this B is the smallest sigma algebra which consists of all open sets in Rn. What is the meaning of smallest sigma algebra? Take any sigma algebra which consists of all open sets. Take intersection of all possible sigma algebra which consists all open sets in Rn. Their intersection is a sigma algebra which gives you this set. Now, can I visualize it? Can I write them down clearly? No. These are basically tools for you to understand what actually is happening. So, you take a mapping X. So, you have again you take X now. So, this is called a random vector. So, random vector. Most of our studies would largely remain for in the domain of random variables, but this is just to give you a generalization. So, in this case the same thing would occur, that if you take any B, now it is a set in Rn which goes to this sort of B, the Borel sigma algebra in Rn, then it implies that X inverse B must belong to U. So, the random variable concept is fundamental because it takes you arbitrariness from the notion of a random experiment. You are always in the setting of a real line, that is the fundamental key idea actually. So, once the key, for example, I can give you one construct as one example. You can create others or see from standard books, and many of you possibly know it. So, you define this indicator function. So, this is just a set indicator function which says that if omega is in A, that you mark it 1, you mark it 0 if omega is not in A. Okay. Now, once that is done, how do I guarantee that this is a random variable? I say chi A is a random variable. So, I am mapping, taking each omega from this and making this definition. So, if I take, so this is in R, so if I take a B from this B, how do I calculate? That is the key question. See, if 1 is in B and 0 is not in B, then this would be in A. If 1 is in B and 0 not in B. Of course, sorry, it will go into the complement of A if 1 is not in B and 1 is not in B and 0 is in B. So, what would happen if, so A is of course an event, this is in U, A hence by since U is a sigma algebra, A complement is in U. Similarly, you can talk about what happens if 0, 1 and 1 is in B and 0 is also in that set B, then what would happen? Then it will become A union A complement. So, and that is also again in A. So, whatever way you say that okay, this is not anywhere, 1 is not in B, 0 is not in B, then it is A union A complements complement. So, then that's why, so that will again be a sigma algebra. So, you can try out. This is one example. Other simple examples are head and tail. When you make a toss a coin, you let us denote by random variable the number of heads that come when I toss a coin. It can be either 0 or 1. That's the sort of thing. So, that is the way you define random variable. Another sort of important way of defining random variable is to construct some random variable out of these indicator functions. These indicator functions play a major role in probability theory. So, this is something one needs to understand and try to get a hang of the ideas. See, what happens here is that, for example, I construct a random variable like this. Now, this sort of thing, it is called a simple function. This also is a random variable. So, you have some set, say 1A to AN. So, all of these are in U. Of course, you can completely, it will completely make sense that this is actually only non-zero. It will, if you take the union of AIs and take omega from there, then it will always give you one of the AIs, otherwise it will become 0. So, this sort of function, this sort of random variables are sometimes called simple functions. a key thing that is sometimes required is the notion of this sigma algebra, which is called a sigma algebra generated by the random variable. You can think this as a random vector, but largely I am talking about the random variable. Does not matter if you think of it as a random vector. You can think x is from omega to Rn. Where B is in the Borel sigma algebra. B. This set is a sigma algebra itself, and this is called a sigma algebra generated. So, it is collecting all the inverse images of all elements in B. So, you take the union of that set, because the collection of all such things would actually form a sigma algebra, which is a sub sigma algebra of U basically. So, this is a sigma algebra. This is called a sigma algebra generated by X. See, X inverse B need not be always giving me every element in U, it will give me some element in U. So, those have a special significance, because they are the ones by which your whole game is been done, because they are linked to random variables. So, they are the stuff that is really required when you calculate stuff. So, this is called the sigma algebra generated. So, I will leave it as a question of exercise to prove that it is truly a sigma algebra. Our question would now turn to a notion of stochastic processes. So, I am just rubbing this idea. So, random variables can be also lined up in the form of a sequence, and these stochastic processes play a very fundamental role in finance, because everything that happens is in financial markets you see changes of certain things over time, and all these changes are stochastic in the sense that they are random, essentially random experiments. So, you take a collection of random variables for each t essentially denotes time, this xt is a random variable. Sometimes some authors write it as xt as x of t. So, we will maintain the symbol xt here, because it is much more helpful for handling certain things. So, this collection, it could be infinite of course, or it could be finite also. So, this is called a stochastic process. So, for example, if you look at this stochastic process, so where St is the price of a given stock, where 0 is the starting time where you know what is St at this current moment, and capital time T is the time when your trading is over with that particular object, and St denotes the price of the stock of a company, a share, one share of a company, unit price of a one single share of a company between this period. Of course, the real issue that lies here is the following. The issue that lies here is that every St, S0 you know, but you do not know what is S of any t which is beyond 0. Of course, you could think this is a very continuous setup. You could think of in our discrete setup, you can think of S of n 0 to say capital N, where each n belongs to capital N, capital N hat. So, basically then you have S1, S2, S3. So, now 0 at time I know the price, but S1 I do not know what would be S2 or what would be S3, etc. So, that is a stochastic process. So, if you take our fixed omega, then you can calculate for each of the different, see as you change the time your structure of the function xt changes. They are different random variables, not the same random variable. So, S1, S0 is of course a fixed now thing is known, S1 and S2 are different random variables, S2 and S3 are different random variables. So, if you take a fixed omega from the sample space and then calculate that ST omega for every random variable, for every t, right, for every t there is a different random variable, you press the omega, then what you would get is a sample path of a stochastic process. So, here what you have done is you have t and here you have say S of t or x of t, does not matter, maybe x of t. So, what you do, you are basically for a fixed omega, you can see how the value of each random variable changes at omega. So, in a market setup, if this was again the stock price ST, then I am trying to see, obviously stock price would not be negative. What I am trying to see is that if I am assuming that for a given some time period, I would have a particular type of scenario, then how the stock prices would change. That is very unpredictable. Assuming that I have the same scenario, my scenario does not change, my market conditions are say at a particular way, in a particular way, then how does my stock price changes? That is something economists want to know, that is something the market people want to know, the brokers want to know. If I change at every t, if I change my scenario, then it is a truly troubled market, it is truly a bizarre market which you can't really handle mathematically. So, the real mathematics is done when you are really thinking that if this is my particular scenario now, how would my prices look like, how would my prices vary. So, if you finally look into, so you know given the particular scenario what would be the price at every time t, but you do not know what scenario would actually come. So, this is called, so what you have done is you have computed x t and omega, sometimes written as x t omega. So, this is called the sample path. So, fixed omega you are changing t, but keeping t fixed, if you change omega, then it is bizarre basically. So, this idea we have just introduced because they are linked to random variable, which we will very soon come, the use of stochastic process would increase in our next discussions. So, here now we are going to talk a little bit of what is the issue of integration and what is the meaning of expectation. Okay. So, simple functions would play a very fundamental role here. So, suppose I have a simple function like this and I define that the integral of this simple function, or every simple function of course is a random variable, because you see actually I have defined a random variable in terms of another random variable. So, a simple function is, then we define the integral of x with respect to the probability measure p as one to क्या था m, 1 to m or nth m, let me write this as m. So, this is the definition. Probability ai is known because these are events, so you know the probabilities of that. So, then the integral is nothing but this. What essentially is this? If anybody has learned some probability, they will immediately recognize that this is nothing but the expected value. But how do I do for, this is for a simple case, very simple setup. Essentially is some sort of a discrete situation, that if you break up the whole thing a1 a2 an, then these are just taking the values a1 a2 an, rest the values are 0. So, I do not need other parts except the parts which are within A1 union A2 union dot 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 AM. So, this is nothing but the value has been taken over those part and the product and the probability. This is nothing but an expectation. So, this is essentially the expectation of x or the average of x of the random variable x. But how do I define this when it comes to an arbitrary random variable and not just a simple function? We define this by using the simple function. This is the way Lebesgue integral is defined. I would ask you to really look up, because we had told in the beginning that we need some mathematical maturity to do this course, but does not matter, that you can still follow by looking at what I am writing. Is that if you have any random variable, then the integral of this random variable, of course you can talk about a random vector, I am not getting, I will just write to you at the end what one can do for a random vector, but this is just for the random variable. So, take so y is my required simple function. So, I am looking at all simple functions which are lying below x. So, this actually means so I am writing it for all omega, it will be enough if it is for every omega other than a null event. So, let us not get into those technicalities, okay, assume this thing. So, this is what is the definition, that you can compute for all the simple cases and then take the supremum and whatever be the value, assuming it is finite. So, assuming that this is finite, and then we said that the integral exists. What is this? This integral does is nothing but a generalization of this idea. You use the simple function idea and generalized it. So, this integral is called the expected value of a random variable x. This of course is defined for x greater than or equal to 0, means a non-negative random variable. Here I just want to mention that AIs that I have taken, so these are simple functions. So, if I am talking about non-negative random variables, some of the y's can be with the situation where all the AIs are non-negative, some can be with some non-negative, some negative. If all the AIs are negative, of course such a y is less than this. So, this definition actually works for a non-negative random variable, that is x of omega. This writing for all omega is not really technically fine, but does not matter for this situation. That is exactly what it means. So, now if you want to talk about what happens for a case which is does not have such sign, then you just have to write, x as x plus minus x minus. So, you can always express a real number as the difference of two non-negative real numbers, and then this is nothing but so that point I missed when I made the definition, but you have to always remember that this has to satisfy this property, x greater than or equal to 0. So, for that we are defining this. Well, once you have non-negativity, a lot of good properties can be proved, and once you have that, then all those can be translated to the other things by this. That's a much easier way of generating properties about integrals. Of course, here we assume that integrals are well known, means these integrals, you know about the properties of integrals, you know how they add up, you know what happens if I multiply a function by a constant, the constant comes out of the integral sign and all those stuff. So, that we will not get into such details here. What we are going to now talk about is that this is what we call expectation. of a random variable. This is what is called the expectation of a random variable, and this is what is called a variance. Of course, these are all very abstract looking things, it does not make sense, and those who have read probability might also start getting confused what is really going on. But the key idea of really studying probability is to know the notion of a distribution function, which tells you how a particular observed random variable would actually behave. So, given a random variable, the distribution function is a real valued function which calculates the probability that once you want to evaluate this f of capital X at x, this calculates the probability that x is less than or equal to x, which means calculating probability of the event, a set of all omega in small omega in capital omega such that x of omega I leave it to you to confirm that these are actually events, these sets are actually new. Because if you look at this, what is this? This set is nothing but x inverse minus infinity to capital S. So, basically you are finding probability of x inverse of minus infinity capital X. And that is why that particular sigma algebra is so important. Why I need to know the distribution function? Because that allows us to understand, it is a cumulative thing, just like you have studied mean, median, mode, you have talked about cumulative effect of certain observations, means we are looking at the growth of x, how much, with what probability it can come under x. So, once I am able to tell you, I am able to give you some sort of an idea about the stochastic behavior of that particular random variable. So, a random experiment is giving me some information, but that is translated in a nice way in this set of our distribution function. I will not talk about the properties here, but I would just like to tell you that associated with every random variable is its characteristic. One is either, usually it is either something called discrete random variable, which it can take only countable number of values or finite number of values, or a continuous random variable which takes non-discrete set of values. And then how do I calculate this? The probability is usually calculated by the means of a density function. This is, I am just recalling the thing, this is something which has to be known in a first year probability course, and once you know this, then expectation of x becomes an easy thing to calculate. So, why do you need the density function? It is very important to know when you have a continuous random variable, you just cannot say that probability of x is equal to x is something. Probability that a continuous random variable picks up just one value is 0. how do you look at it? What is the intuition behind it? I am not going to write down the detailed description, I will just tell you an intuition behind it. The intuition is the following. You take the real number 0, 1. Now you are arbitrarily picking up a point from that set. So what is the probability that x equal to half? So what is my favorable outcome? How many objects I have in that favorable outcome? 1. And but I have huge, infinitely large all possible outcomes. So you can immediately understand that probability is 0. That sort of, this is not a mathematical explanation, but this is just a rough intuitive idea, but intuition is anyway a guide to mathematics. So this density function plays a very important role, and now what I will do is I will introduce to you the notion of independence, and by introducing you to the notion of independence, I will actually stop my discussion. So we will talk about conditional probability, because we are going to talk about conditional expectation very soon. So it is very important that we talk about conditional probability. I have some notes written down which can be scanned and later on put into the web. So what is conditional probability? So let me now talk about this very important issue in conditional probability asks how would the probability of one given event A be if I know that some other associated event has occurred. Mathematically it means the following. Mathematically it means that I have a probability space and I have two events, and it implies that and also I know that probability of B is strictly greater than 0. That B can occur with a positive probability, right. Now suppose B has actually occurred. So what is the probability of finding A knowing B? So which is symbolized like this: probability of finding the probability of A given that B has occurred. And of course you have to assume this, that B has a finite probability of occurrence, a positive probability of occurrence. So what does this actually mean? It looks very fishy that you are just using language to talk about this. It means that if I choose an omega in B, so B is a element in U, so it is a subset of the sample space, so I can take some omega from B, assuming they are non-empty of course, because an empty set would, Bu cannot be empty set because otherwise the probability would be 0. So I am choosing an omega from B. The question what we ask here by asking this a probability A given B is what is the probability that omega is also in A? That is the question. So here you have your omega, and here you have your A, and here you have your B. So if omega is in A, what is the probability that omega is in B? So omega must be in an area where A and B both can occur. So we then have to think of joint occurrence of events, right. Now if I want to define this probability, this is not the same probability as the one I have defined there, because that only talks about probability of event A, of probability of events in U. But what does this, where does this probability, where does this event stand? Where is sigma algebra? Where is the sample space for this? So when I am looking at, so my question again is very important, and I am talking about if omega is in B, that I know that this omega has occurred, what is the probability that it is also in A? So then A given B is an event which is not really a part of this sigma algebra. These are just events A and B, A, B, C, D, but here I am talking about something else. So which means I really now have to consider a new sigma algebra and a new sample space here. So I am only bothered about those omegas which have occurred in B. If they have not occurred in B, I am not bothered about them. That is why the talk that I am looking for A given that B has occurred. So we are only looking at those omegas which have occurred in B, which have come up in B. We are not looking at other omegas, and thus B is taken as my new sample space, which I mark as this. And what is my U tilde? U tilde is C intersection B, where C is element of U. So B has to be related to all such events. So you see joint occurrence must now come if you are going to talk about conditional probability. Okay. Now I define by P tilde the following probability measure. P tilde I have to put some event in by P of B, which I know. But A intersection B is actually an event in U. But here I am considering some sort of subset of the events in U. Now if I want to consider P tilde of A intersection B, that is under this new probability measure, what is the joint occurrence of A and B? That is exactly what we are seeking, a new probability measure. Now my sample space has changed, it is no longer omega, but it is omega tilde, which is nothing but equal to B, the event B, right. So then this is by this definition equal to probability of A intersection B, and we mathematicians define that P tilde of A intersection B, P tilde of A intersection B is also defined as or said to be the probability of A given B. And that is essentially the meaning of conditional probability. So this is nothing but P of A intersection B by PB. Two events are said to be independent if it does not matter whether omega was in B or not. The fact that omega can be in A, that probability is independent of the fact that omega has come up in B. That is the meaning of independence of two events A and B. So if two events A and B are independent, that is the probability of occurrence of one does not affect the probability of occurrence of the other. Here the probability of occurrence of one affects the probability of the occurrence of other because the sample space gets completely changed. So A and B are independent if probability of A intersection B is probability of A into probability of B. So that is it, voila, and with this we stop our discussion today, and next class we are going to talk about Chebyshev's lemma, Borel-Cantelli lemma, and some surprisingly interesting facts. Okay, thank you very much.